Hello, good day. Today we're going to discuss electrostatics. We're going to deal with electric charge, the Coulomb's law, the electric field, and the electric flux. This is our first topic for the third quarter for this second semester. So let's start our discussion. Electrostatics is the study of static electricity, which means that it is the electricity at rest. Static electricity involves electric charges which arise from particles of an atom. We have excess charges that makes hair of that young boy to go up. So that's your grade 7 science, don't you think? So we're not going to deal with it anymore. So we're going deeper as we study the atoms and the particles that surround us. And this electrostatics will give us an idea how electricity is being around us and how we are able to use it on our daily life. So the electrostatics will just give us an idea on how to study the Coulomb's law, the electric field, and the electric flux. Let's take note that the particles of an atom are just this, like particles that's moving around of a certain something. And these particles of an atom consist of these different uh, structures. We have the proton, then we have the neutron, then we have the electron. Okay. So these particles consist of this atom will give us an idea on how the electric charges are passing and how it affects each one of the particles. So, ang mga particles na ito ay may iba't ibang location na nakikita sa iba't ibang atom. Let's take a look into this table. The particle proton, which is inside of the nucleus, as well as the neutron, which is also inside of the nucleus. The mass of a proton is equal to 1.6725 times 10 raised to negative 27 kilogram, which means it's very, very small and it's too light. While neutron, on the other hand, it has a 1.6749 times 10 raised to negative 27 kilogram as its mass. But if we're going to take a look, the charge of the neutron is none, while the charge of the proton is a positive 1.6 times 10 raised to negative 19 coulomb. This positive charge makes the nucleus as a positive charge as well. Likewise, on the electron, which is around the nucleus or surrounding the nucleus or moving around the nucleus or outside of the nucleus, has a mass of 9.1095 times 10 raised to negative 31 kilogram, which means it's much lighter compared to the proton and the neutron. And it has a negative charge of 1.6 times 10 raised to negative 19 coulomb. They have the same amount of charge with proton but in different direction, in different magnitude or different in symbol. Proton is positive while neutron is negative. To clearly understand how particles interact with one another, let's try to study Coulomb's law. With this video by Crash for Physics, we'll try to discover how Coulomb's law is greatly affected, or how this Coulomb's law affects, or how this Coulomb's law will uh, states, and how this explains the relationship between the moving or at rest particles. Let's try to watch. So sorry for that. We had a technical difficulty there. So we had that the electrostatic force can be calculated through the number of through the value of the charged particle and the distance that separates them. But let us take note that according to our guest speaker, if the force is equal to positive, they both repel. If the force is equal to negative, they both attract to one another. So here, we will notice that the attraction and repulsion depends on the magnitude and the sign, whether it's positive or negative for both the charges. So here, the Coulomb's law is just stating to us that that the force of attraction or repulsion between two small charged bodies is directly proportional to the product of the charge and inversely proportional to the square of the distance between them. Meaning to say that the SI unit for charge, which is denoted by this small letter Q here, is in Coulomb, named after Charles Augustine de Coulomb. We can calculate for the electrostatic force by using this equation. F is equal to the Coulomb's law constant, which is K, multiplied to Q1 times Q2 divided by D squared. Let's take note that the value of K, or the Coulomb's law constant, is that it is 9.0 times 10 raised to 9 Newton square meter per Coulomb square. So this is the constant value that we're going to use if our two particles is within a vacuum or in air. Now, looking into this animation by Pet Colorado, so we have here this simulation for Coulomb's law. So we have two charges here with different magnitudes and different uh, signs, one with negative and one with positive. So you will notice that there is a force of attraction that is happening to them. So if we're going to make the charges equal to 0, so there's no charge at all, both charges are zero. So if one charge is, for example, I have here 5 microcoulomb charge for charge 1 and another 5 microcoulomb for charge 2. So you notice that the arrow here, the vector here, vector arrow here is pointing to the left while the arrow here is pointing to the right. So you notice that the force on Q1 by Q2, it is given that it is the force exerted by Q2 to Q1, which means that it is the force exerted by this charged particle here to another particle. If I'm going to change the charge of Q1 into negative, so we'll have a negative 5, you will notice that both of them attract one another by, we have here the force by of Q1 or on Q1 by Q2, it's pulling Q1. While on the other hand, Q2 is being pulled by Q1. So they are pulling one another. That's why they are attracted by one another. So this is how we able to see it. Let's try to have the atomic model. So we have negative 2e here and 4e. So you will notice that if we separate them much farther, the force of attraction is getting smaller. But if we're going to put them or place them very near to each other, so you'll notice that the force become much greater compared to the ones that we had before. So if we're going back to the macro level, we're going to put them near to each other, you will notice that the vector here, the force here is much greater if they are near to each other than when they are apart. Let's take note that the distance is inversely proportional to the force exerted by the two charged particles. So the farther they are, the lesser the force of attraction or repulsion. So the nearer they are, then the greater the force of attraction or repulsion. So let's have this example number 1. Calculate the force of attraction between the lone electron and proton in a hydrogen atom. The average distance between these two particles is 5.0 times 10 raised to negative 11 meter. Let's have the given. We have the Q of E is negative 1.6 times 10 raised to negative 19 coulomb. And then we have the Q of proton is equal to positive 1.6 times 10 raised to negative 19 coulomb. And their separation distance is 5.0 times 10 raised to negative 11 meter. Let's take note of the K constant or the Coulomb's law constant of 9.0 times 10 raised to negative 11 meter. And then, sorry, that's Newton meter squared per Coulomb squared. So we have to identify the force of attraction between the two charged particles. So we have F is equal to K, Q1, Q2 divided by D squared. So we have F is equal to 9.0 times 10 raised to 9 Newton meter squared Coulomb squared. This is negative 1.6 times 10 raised to negative 19 Coulomb. 1.6 times 10 raised to negative 19 Coulomb. And then we have 5.0 times 10 raised to negative 11 meter. Then we square it. So the next step now is to multiply everything. So we have now F is equal to it's 9.22 times 10 raised to negative 8 newtons. So negative times positive, it's negative. So we have here the negative sign, 9.22 times 10 raised to negative 8 newtons. Since both they have a negative answer, so this gives us the final answer that they are at the point where they are in the attraction mode, or the force that have between them is the force of attraction. We're going back to what I have written a while ago. If it's negative, diba, it's attraction. If the force is positive, then it's repulsion. Okay? So moving on, so to identify how this force of attraction clearly is being stated to us, not just by the Coulomb's law, it's something to deal with how the forces are being distributed within the region where these two particles are present. So we try to learn more about the electric field. So let's try to watch this video clip as we unpack and learn this uh, concept of electric field. So there no sound. So it was by Michael Faraday. It's a region. Let's take note that the electric field is a region of space where the electric charges are present, and it is a measurable effect generated by any charged object. So we have here a point charge as a test charge that we are going to use. So electric field is equal to force divided by the magnitude of a test charge. So we will use this test charge, and the force that we're going to use is from the Coulomb's law. So to put Coulomb's law in the electric field equation can cancel out the test charge there, and we can come up with an equation E is equal to K Q over R squared, or D squared. So we have these charges. Let's take note that the positive charge, and we have this point charge or the test charge here. The positive charge, let's that the arrow or the electric field lines move out of the charge, while the negative one moves or comes in to the charge itself. So the electric field lines will determine the force of attraction and repulsion based on this magnitude. So our Q charge there is the big positive charge, and the test charge will determine whether it's a positive or a negative charge. Let's take note that the negative charge is So here is a dipole, which means that one particle is moving to the negative charge. So there is the four important properties of electric field lines. So here we were able to take note that all points and all electric field lines from the positive charge moves to the negative charge. Yeah. So that's the direction. It always moves to the negative charge. And there are no lines. There are no lines that is being crossing one another, which means that no other electric field lines can superimpose one another. So let's take a look on this simulation from PET, how we are able to distinguish the electric field line. So before that, let's take note of the definition of electric field. It's a region around a charged object or particle where the electric force can be determined. And we can calculate for the electric field intensity into E is equal to F over Q, where E is your electric field, F is the electric force or electrostatic force, and Q is the charge of a particle. So based on the given form equation a while ago, we can state here that this F here can be from the Coulomb's law. So we have E is equal to the F, which is equal to K is Q1. Sorry, let's change this Q. So we have here Q1. Then as our charged particle Q2, and we have D squared over Q. So this point charge here, this our test charge can cancel out. So we can calculate E for a lone charge is equal to K Q over R squared. This equation is only applicable if there is a lone charge. Ibig sabihin, iisang charge lang ang meron. If there are two charges that's present, then we use this equation. Okay? This is for two charges present. So this is for 1 only. Let's take note that a positive Q, the movement of the electric field line is outward. So this arrows here is called as the electric field lines, and it's pointing outward from the charge itself. So the electric field from an isolated positive charge. On the other hand, if we have a negative charge, the movement now is inward. That's why the diagram that I have written a while ago is that the positive is always moving to the negative. We always tend to move to the negative side of the particle. So all these field lines are moving or coming out from the positive, and it's always looking for the negative. In these two diagrams, we have here dipole uh, electric charges. So we have this, the first one in letter A, we have a positive charge and a negative charge. So you will notice that it's moving towards the negative, and we have here an attraction. On the other hand, in letter B, you have here 2q, which means that the charge, the magnitude of the charge of the particle is much greater compared to the other particle. And you notice that they are near to each other. So the electric field intensity here in these field lines are much greater compared to those who are far from the charges, which means that the electric field within this region is much greater compared to the electric field on the other parts where there are no charged particles present. Now, according to the video clip that we have watched, the charged particles of both charges, same pole, diba? Same charge, positive, positive, they will not superimpose with one another. That's one of the law of these electric field lines. They will seek for a negative charge infinitely as long as they will able to seek for the negative charge. So you will notice that this area here gives us an idea of repulsion. So if it's a negative, you will notice that it will also repel with one another. So let's try to look into the animation that I'm talking about. So we have here on this animation from PET, the charges and fields. So I will place one charge of positive nanocoulomb. So we have here, you will notice that the arrows are pointing outward from the positive charge. So I will place another positive charge here. So you will notice that the arrows are still pointing outward. And if I'm going to place near the charge to one another, you will notice that the arrowheads are not pointing, or they are not moving along with the same direction. I mean, they are not superimposing one another, even if they are very near with one another. I will replace it with a negative. You will notice that, diba? If I have here a lone charge particle, all of the electric field lines are moving away from the charged particles. But if I'm going to place a negative here, you notice that it bends, moving towards the negative charge particle. So, papunta sila lahat doon. So it's a clear description of a force of attraction. So if we're going to move it a little farther, so makikita natin yung mga electric field lines na moving towards this region. So yung medyo malayo, you will notice on the grayish and shadowy part, yung electric field intensity ay lesser compared dun sa electric field intensity na kitang-kita natin na yung mga arrows. If I'm going to place a sensor here, this is a point charge. This determines where the electric field intensity is greater. Mas malapit siya sa point charge or dun sa ating charge particle, mas malaki yung arrow na nakikreate. So that's the electric field intensity. Habang nilalapit ko siya sa negative charge, you will notice lumalaki ulit yung kanyang value or yung ating arrow. So if we are going to move a little farther, you notice that it diminishes until it fades out. So you will notice that it always seeking the negative, the point charge itself. Because this sensor here that I have is on a positive. Okay? So, lagi siyang away from the positive. At ito naman, lagi siyang moving to the negative. Mas malapit, mas malaki yung electric field intensity. Mas malapit, mas malaki. Mas malayo, mas malaki. Still following Coulomb's law. Okay? So let's have an example to calculate. So we have here a 0.50 microcoulomb charge was placed on a near charge body while experiencing a 0.20 Newton of force, and we want to identify the electric field intensity of the charge particle. So here we are given with a charge equal to 0.50 microcoulomb, where it is equal to 0.50 times 10 raised to negative 6 coulomb. And we have the force, which is equal to 0.20 newtons. So our electric field intensity is equal to the force divided by the charge particle. For our solution, we have E is equal to 0.20 newtons divided by 0.50 times 10 raised to negative 6 coulomb. The electric field intensity is equal to 4.0 times 10 raised to 5 Newton per coulomb. Let's take note of the SI unit of the electric field intensity, which is Newton per coulomb. Moving on our discussion is the electric flux. Electric flux is a measure of electric field perpendicular to a surface. So by definition of the electric flux, so we have here the electric flux is denoted with a Greek letter phi. So the electric flux is equal to the electric field intensity multiplied to the area times cosine theta. The SI unit for electric flux is Newton square meter per coulomb. So you will notice that when we say perpendicular to the surface, the area of this surface where it is placed on a horizontal, you will notice that the electric field lines are perpendicular to this surface. Why is it cosine theta? You will notice that this area that I'm talking and I'm referring to is where the electric flux will pass through. So to have a clear instructions and clear definitions of electric flux, let's watch this video clip. So here we have that if the angle is not perpendicular, therefore there is much lesser of the flux or the electric field lines that will pass through the surface.
And or straight ahead, if it's not straight perpendicular to the surface, the flux actually decreases even if the number lines are stay.
So we have here that the example number 4. Let's take note that the electric flux will have to move on a perpendicular, another perpendicular surface. So when it's not on a parallel with the another, sorry, with another part where the electric field lines or the density of the electric field lines will pass through, then a lesser amount of flux will be present. So based on this, we have a given of electric field intensity of 8,000 newtons per coulomb in an area of 10 square meter. And then the equation for electric flux is E A cosine theta. And that we have just to substitute the given values. So we have E is 8,000 newtons per coulomb, and then we have the area which is 10. And you will notice that the angle here is at 0 degrees, so cosine 0 is 1. So we have the electric flux equal to 8.0 times 10 raised to 4 Newton square meter square per coulomb. So this is the answer. Let's have example number 5. What is the electric flux of a uniform electric field is equal to 5,000 Newton per coulomb passing through a flat square area of 2 square meters at an angle of 60 degrees. So you will notice that if this is the horizontal, we are talking about that the surface area should be perpendicular to the horizontal. Since it's already at 60 degrees, there will be few number of electric field lines that can pass through this certain area. So we have a given of 5,000 newtons of E newtons per coulomb and an A of 2 square meter. And we have an angle theta of 60 degrees. So again, our equation E A cosine theta. So we have our solution. The electric flux is equal to 5,000 newtons per coulomb times 2 square meter times cosine 60. Cosine 60 is 0.5. So we have now the flux is equal to 5,000 newtons per coulomb to square meter and zero point 0.5. So the electric flux is now equal to 5,000 Newton square meter per coulomb. So this is the amount of electric field lines that pass through to that kind of surface. So to end up our discussion, let's go back into our summary. Let's take note that electrons have a negative charge and protons have a positive charge with a magnitude of 1.6 times 10 raised to negative 19 coulombs. Then the unit of charge is in coulombs, which is denoted as capital letter C. And a charge is conserved and quantized in units of E. Insulators do not allow electrons to move between atoms, and conductors allow only electrons to flow freely. The force of attraction between electric charges, or rather the force between electric charges, is along the line connecting them. And let's take note that like charges repel and opposite charges attract. Based on the Coulomb's law, we have given this magnitude of the force of F is equal to K multiplied to the product of Q1 and Q2 divided by the R squared or the distance squared. Let's take note of the K constant or the Coulomb's law constant of 8.99 or 9 times 10 raised to 9 newtons square meter per coulomb squared. And we have that the force exerted by several charges act as a vector, since it's a vector quantity. A spherical charge distribution behaves from the outside as through the total charge were at its center. And electric field is the force per unit charge or a point charge. We can calculate it through the use of this equation. E is equal to kq over v squared or r squared. And electric fields created by several charges again add as a vector. Same as with the forces a while ago. Electric field lines help visualize the electric field itself. Then the lines or the field lines point in the direction of the field, and it starts from the positive charge or infinity and end on the negative charge or infinity and are denser where E is greater. Dun sa pinakita nating illustrations and simulations kanina, you will notice that it's greater there when it's near to the charges. And an electric field within a conductor is zero in if charges are in static. And lastly, electric field or electric flux through a surface can be calculated as phi is equal to EA cosine theta. That's our discussion for this moment. So that's electrostatics. I hope you learned something. If you have question, leave a comment down below. See you and have a good day.